Okay. Okay, good afternoon to everyone. We can start this session, technical session 9.3, on safety risk and operation of the ground infrastructure. I'm Carmine Todaro. I'm an assistant professor at Polytechnic of Turin. And I have the pleasure also to introduce my colleague in this role, Konstantinos Sakas. And we will have this afternoon session with 4 different presentations. I just want to remind to stay in 15 minutes, then we will have 5 minutes of questions. And we can start with the first contribute. The title is Monitoring of Compressed Air Workers During Hyperbaric Intervention in TBM. And I would to invite on the floor Dr. Nina Subotina. Nina Subotina is graduated with honor in the first Moscow State University in the URSS. She's expert in hyperbaric medicine, and from 1998 to 2018, she was medical director and president of the Center for Hyperbaric Medicine of Buenos Aires. She was medical advisory contractor by company Pilos Trevi and the medical advisory contractor for compressed air work in consortium collector Manche of Gela. So I think that we will have a very interesting presentation for one of the main experts in hyperbaric topic. So Nina, the floor is yours.
Thank you very much. For me, it's an honor to present this work here. So, monitoring of compressed air workers during hyperbaric interventions in TBM. Okay, the progress made in tunnel construction with tunnel boring machines in urban areas and difficult grounds points to the compressed air worker as a main figure. They are the ones that should carry out the maintenance of the cutting wheel, working in the hyperbaric environment and dealing with all the risks associated to such activity. They have not only to perform their duty perfectly, but also they have to care of their personal health to cope with growing working pressures and more complex tools and tasks. Compressed air workers should be reliable and capable individuals in all aspects. While health problems in high-pressure environments are usually considered in limits of presence or absence of dysbaric syndromes, other important details of the worker's health, such as their everyday mood, strengths, and physiological functions, are usually not taken into consideration. Okay. So, in the Riachuelo System Project, Gela has implemented a package of good practices for dry hyperbaric environment that included the medical and safety procedures, the detailed workers' health studies, vital signs, cardiovascular parameters, and psychology, the records of bubbles in the blood after surfacing in high-pressure interventions. Why it is important? It is important because while the quantity of circulating bubbles is low, also the risk of decompression sickness is also low. In Argentina, for the first time, were applied the German and French hyperbaric protocols that were not applied before. Here are the protocols mentioned. So, to justify the use of these protocols and their conveniency to applying in the local environments, they were used the Doppler bubble registry. So electrocardiograms and Doppler scanning of the precordial and subclavial zone were analyzed using the Kissmann-Mazurel score. It's here. On the, you see? No. Pardon. Here, which range from 0, no bubbles observed, to 4 bubbles fill the entire space of the heart chambers. And this video, I will look how to put it on. It is the heart, and there are seen some bubbles. That bubbles are grade 2, only grade 2. But the quantity of bubbles is calculated as acceptable when no more than 20% of the bubbles of the grade 3. So, medical support of the hyperbaric intervention implemented by Gella included, first, the review, pre-intervention and also after surfacing, all these parameters that are listed here. And besides, the physician also observed the movement, the behavior of the compressed air workers, and it was necessary to diagnose or to rule out the probability of some hyperbaric interventions. Here are the results. Average values of vital signs before and after the intervention, and that a number of observations. You see that there are many observations were made. We see that the blood pressure, systolic and diastolic, is slightly lowered after the intervention. And the heart rate slightly increased. But the difference, look at the difference. It is statistically significant only because of great number of observations. But you see, the difference between 120 and 160 millimeters of mercury is 4 millimeters of mercury. It is less than 5 millimeters that are considered within the era of measurement. So it's statistically significant, but practically, physically, it is not important. And also with the heart rate here, 74, increased to 78, also that has not important physiological significance. So our first conclusion, that the safety of the working environment and the organization of the working schedules was proven. All the physiologic and psychological parameters of the compressed air workers were perfect. Our experience was analyzed, and we wrote it, and it is presented in these books, one in Spanish and other in English option, and both are available at Amazon. The second issue was the trend, the tendency in the changing of the parameters. You see here the segmentation by pressure. Here is the pressure till 1 bar, from 1.1 to 2.3 bar, 2.4, 2.5, and the most highest 2.6, 3.6. You see that the tendency is to lower the absolute value of the changes. So, how to interpret? The interpretation is challenging. We should compare with other studies about the cardiovascular system response to the high pressure. But we have not found any data of the similar situation. But there are many publications of other working situations, for example, in aviation and other type of working, when the working is a very stressful and a very demanding. So we analyzed two parameters, the duration of the intervention and the pressure. Here you see the total time of intervention, and here are 2 hours, 4 hours, 6 hours, 9 hours. We see that the total duration of intervention didn't show us any differences. The same with the difference of the bottom time. It was the bottom time also no difference as we saw in the main slide. But decompression time, yes, showed that with the less time of decompression, it was more changes, and with the at the most time of decompression, the changes were less. And here I put the segmentation of pressure. We see it's the same as the duration of the compression time. Effectively, they are closely linked. So, how to explain it? How does the cardiovascular system respond to high pressure, and which criteria should we apply? The stroke volume and cardiac output parameters are used to characterize working condition in different demanding and stressful situation. So it's important that when the greater is the energy consumption during work, the more pronounced is the alteration of the cardiovascular system. So we had to compare the stroke volume and cardiac output of our workers in the different segments of pressure. I will remember you that the stroke volume is the volume of blood pumped out of the left ventricle of the heart during each systolic contraction, and cardiac output is the total blood volume pumped from the left ventricle per minute. So, as according to bibliography, the long-lasting working day and psychophysiological stress produce a reduction of cardiac output, affecting both parameters, heart rate and stroke volume. But in our group of workers, only 1 from 16 showed a similar reduction. And here are the data of the stroke volume and cardiac output before and after intervention of all the group, of all the 16 persons. And we see that the cardiac output has not changed significantly from the initial values. What about nitrogen narcosis? Probably it was due to euphoria caused by nitrogen narcosis. The mood registry was done after the decompression, but the physician observed during all the time of all the intervention the behavior of the workers, and there were not observed any nitrogen narcosis effect in the behavior of the workers, and there were no incidents, labor incidents at high pressure. What is important that our workers have received a special training on nitrogen narcosis. This is the photo. If somebody is interested, I can explain. So, Minor changes of vital signs at high pressure could be due to relative hyperoxia. We know the classical work of Eichenhoff, who in 1984 presented that the bradycardia is linked to relative hyperoxia and increased pressure. There are also
Sorry,
are there
Dr.
also-
Nina, 2 minutes.
Okay,
We have.
okay, I will finish.
Thanks.
Okay, so our workers worked at 2.6, 3.6 bar, so it was equivalent to 3.6, 4.6 ATA. So breathing air, they had almost 1 atmosphere of oxygen. So detailed studies showed that the hyperbaric intervention in TBM at pressures up to 3.7 bar are well tolerated and don't present any special risk to the health of the compressed air workers according to the parameter studied. All the measures that were invented by the Gella in the Riachuelo project gave its result. It was the systematic process of personnel selection, specific training, strict application of compression-decompression protocols, and everyday medical support. So the Gella Safety and Health Department relied on the analysis of hierarchy of controls pyramid to carry out these procedures, and the medical studies presented here helped to include the necessary control measures to eliminate or mitigate the risk. So this approach ensured that the project was carried out successfully, and the safety and health of the workers were protected. Thank you for your attention.
Thanks, Dr. Subodona. Are there questions from the floor? I know that maybe the topic, we are engineers, so we are not so... I have, anyway, a question. It's just a curiosity, so you can forgive me if I will use words not so perfect according to a medical point of view. But when you listed the check, you,
Yes.
told also that the mood and the behavior is considered for the pretest, yes?
Yes.
But how
Not pretest, not.
Not pretest.
The gait and the movement also. If somebody came and has some problems, also it's probably the physician is observing the before the intervention.
Okay.
He will have his blood pressure, heart rate, drug test. So if his behavior is rare,
I just was...
but after, it's very important after, because sometimes the bends make that the person has, for example, his arm with the pain in the arm, and so they have a special position. Why it is called bends, from the verb to bend, to incarvarse. So it is one of the tests that the physician who is trained in hyperbaric medicine could diagnose, or probably think it could be, because during the 24 hours after the intervention, our physicians were on call, because any symptomatology could arise after the intervention. Generally, 60% in the first hour, 90% in 2 hours, but till 24 hours, and also as extremely rare 48 hours. So it could appear something.
Okay, thanks a lot. Okay, if we have no other questions, maybe Nicola. Thanks.
Okay, so welcome from my side. My name is Konstantinos Sakas. I am a Doctor of Mining Metallurgical Engineer, holding a PhD on Material Science, and currently I'm a Managing Director of Enalos PC. I have the pleasure to invite Ms. Konstantinou, who will present us the available safety egress time estimation through fire dynamic simulation for various cases of fire incidents in rail tunnels. It is a project carried out from our experienced team between Ms. Konstantinou, Dr. Kayanotis, and Professor Bernardos. Ms. Konstantinou is a PhD candidate at the School of Mining and Metallurgical Engineer at NTUA, National Technical University of Athens. Her PhD is focusing on risk analysis during evacuation in underground spaces on emergency situations. She also holds a diploma in mineral resource engineering and Master of Science in Design and Construction of underground works, the MSc in Greece. Currently, she works at the Ministry of Infrastructure and Transport in Greece in road construction as a geotechnical engineer. Her research interests are focusing on risk analysis, fire safety, evacuation, and self-rescue in underground structures and the geotechnical engineering. Thank you. You have 15 minutes.
Hello, everyone. My name is Despina Papakonstantinou, and I will talk to you today about asset estimation through fire dynamic simulation for various cases of fire incidents in rail tunnels. Well, when performing a risk analysis, the first challenge is that there is no specific guidance regarding the selection of fire size and other parameters like fire duration or burning materials. However, these parameters are very important because they affect the available safe egress time, which is the time when the conditions become untenable in a specific space. So here, several rail fire cases are selected, and a fire dynamic analysis is conducted, and the reach of each scenario produced for the occupants is presented through an index called the fractional effective dose. Also, the influence of the key parameters on tenability conditions is discussed. In an evacuation analysis, the aim is to ensure that the available safe egress time is greater than the required safe egress time with a margin of safety. FED is used for the determination of the acceptable safe egress time, as it represents the dose received by the occupants in a certain period of time, which may lead to incapacitation and death. As we've seen from the equation, if a FED exceeds the value of 1, then conditions become untenable. The NFPA, the standard NFPA 130, proposes a value for the FED threshold limit of 0.5 for the healthy adult population, while 0.3 is a typical limit in order to provide safe egress for the more sensitive populations. So, based on the above, 4 toxicity risk levels were created based on FED of toxicity. This level varies from the desired risk level, which means that the dose of toxic products is too small to cause problems to the occupant's health, to the not accepted risk level, which means that almost all the occupants in a space receive a dose of toxicity, which makes them unable to perform evacuations by themselves, in other words, self-rescue. Since this presentation is oriented to rail fires, I will present you some of the main characteristics of the fires on rail carriages. So the main reasons of ignition are mechanical and electrical equipment failure, which leads sometimes in severe consequences. Also, a human action, an accident, and arsonism, while it's rare, but it has produced some of the most severe consequences in rail fire history. The most valuable information about rail fires we get from the real-scale tests on rail carriages. Here we have 10 fire curves from these tests, some are very known, like the Eureka test, the Metro Project test, the Carleton University test. We see that the maximum heat release rate, which is one of the most important parameters in fire design because it's actually the size of the fire, varies between 7 and 77 megawatts, and it's achieved from 5 to 118 minutes. So as we see, there is a wide range from this test regarding the HRR max and the time achieved. Here we have the main materials used in rail body that may behave as burning materials during the fire, and their stoichiometric yields, which affect the tenability conditions because it's actually the mass of toxic product produced during combustion. And here we have the fire growth rate, which indicates the time when the HRR reaches its maximum value, and that comes from the Eureka full-scale test in a train and a metro carriage. So a parametric analysis has been conducted in order to identify the parameters that affect the conditions. The calculations are conducted fire dynamics simulator, which studies fire and smoke propagation and the effect on fractional effective dose of toxicity is examined, and also the influence of the main parameters. Overall, 52 scenarios were examined, but here we will discuss only a few of them. So the parameters considered are, as we said, tunnel width and height, the HRR max, the fire growth rate, fire decay phase, the combustible material, and the flammable area. A tunnel of 300 meters length was chosen. The fire fades out in 12 minutes. The simulation time is set to 30 minutes. And the main material used was the fiber-reinforced plastic polyester. Here we have the fire curves used and the fire sizes. So 9 tunnel geometries were examined for 10 and 15 megawatts fire, and also an ultra-fast to a beyond ultra-fast growth rate was compared. The FRP performance was compared to the material polyurethane. The decay time was extended from 12 minutes to 30 minutes, and the combustible material area was set from 10 to 20 square meters. To extract the results, the fed toxicity was measured at appropriate points with distance 50 meters between them at a height of 1.8 meters. And here you see the 3D model and the stratification of the smoke inside the tunnel, and the carbon monoxide concentration at the time 7 minutes after fire ignition. So here we move to the results of the analysis. First, we have the effect of HRR and geometry on fed toxicity. And as we see, the smallest geometries, especially the tunnels with a height of 4 meters, produce the highest fed values. Also, the increase of HRR from 10 to 15 megawatts has a substantial effect on the fractional effective dose. So this is very important for metro tunnels, which are smaller than our tunnels. We see that even a small change on HRR has a great effect. And we see that for a height above 8 meters that we are on the safe side according to the NFPA 130. So here we have the comparisons of the two materials, and as we see, the FRP presents a higher value of FED than polyurethane, as it has a higher stoichiometric yield of carbon monoxide. And as we see, the second chart, the size of burning area doesn't have an effect on FED as long as the fire size remains the same. So here we have the two different fire growth rates, and as we see, even the fire growth rate has not as a great impact as geometry or HRR. It has an effect on the fractional effective dose, and it should be taken into consideration, especially when the FED curve lies near a threshold limit. And regarding the decay phase, we see that when the fire lasts longer, the FED is higher, and the FED curve changes as FED continues to increase with time. So the analyzed geometries for the two fire sizes are categorized into the risk level based always on FED toxicity. The performance of each scenario is a combination of each geometry and the HRR max. As we see, the tunnel section with height 4 meters belong to the non-desired and not accepted risk level, while only 2 scenarios analyzed with the 10 megawatts fire don't belong to the desired level of risk. And here I have the ACID for the scenario that the fractional effective dose exceeds the threshold values during the analysis time. Here we see that the ACID for value of FED 0.3 is between 5.5 and 10.5 minutes. The ACID for FED value 0.5, it's between 7 and 20 minutes. And only one scenario resulted FED 1 at about 10 minutes. So we move to the conclusions. As we say, the tunnel height plays an important role on toxicity conditions, especially for higher maximum HRR value. Specifically for the same section area, FED is 37% higher for the section with the lower tunnel height. So to maintain safe conditions for the passengers during an evacuation, good practice would be to have a tunnel with a minimum height about 6 meters. The burning material, the fire growth rate, and fire decay period have a considerable impact on FED and affect the results on toxicity level. These parameters interact with each other, so cannot be considered separately during an analysis without taking into account the values of the other parameters. So the engineer should take into account all these parameters in order to select a representative fire during a risk analysis. And through an FDS analysis using the appropriate scenario, as it can be estimated for various types of underground spaces. Here, for the cases we saw that within a time frame of 5 minutes, the threshold limit of FED wasn't reached, so we could say that that was an available safe egress time. Thank you for your attention.
Thank you very much, Mr. Konstantinou. Are there any questions?
This topic is very important because the fire in the tunnel, the fire in the metro, the fire in the hyperbaric chamber is especially designed and especially investigated topic. First question, you only look about the carbon monoxide, but you never mentioned such a gas as cyanides, because if you have polyurethane, so you have nitrogen, And when you have nitrogen, so the gas, the cyanide, will be formed. And probably the cyanide will produce more rapidly death than carbon monoxide. With carbon monoxide, you can save the person. With cyanide, it's the question of minutes. So what do you think about it probably in your future research? You can add the danger of cyanides.
Yes, you're right. The cyanide is the second, with the carbon monoxide are the two main reasons of death during fires. Here we dealt more with toxicity fed, which is based on carbon monoxide concentration, the effect of carbon dioxide, and the effect of hypoxia, because it's the diminution of the oxygen in humans' blood. That's what we studied here, yes. So there is the fate of irritants. That's another fractional effective dose for the hydrocyanide that we count, and this is a work in progress. So we also examine visibility and thermal effects. But now we presented only a small part about toxicity, which we make. We made more calculations, and it was more well prepared for, yes, to present.
Okay,
Yes.
very nice, but I repeat my advice to include the cyanides, because, yes, when we have only carbon monoxide, we can save the people. But if we have cyanides, the people will die in minutes. You will not have these 10 minutes to go out with these people. So probably some materials could be limited as polyphenolurethane, which is containing nitrogen. Yes, but very important work. My congratulations.
Yes, these materials are used on seeds and the lining body very often in trade, so we had to take them into account.
Thank you very much. Any other questions? There is a question there. Yes.
Συγχαρητήρια Δέσποινα, congratulations.
Aristo, thank you.
I'm Georgios Giallas, head of underground for Lombard Engineering. I wanted to ask you, have you investigated any effects of the ventilation in the tunnel in your models? And this 7 minutes is the self-evacuation time given by the standards, or it was a typical value for the...
Well, yeah, to answer your first question, this was mainly an analysis to examine the other parameters that we insert to the model to our scenario, mainly, our fire scenario. Ventilation, we had made some also for ventilation, but it was not the main topic because it has a whole other way to deal with it. It's a whole study to study ventilation. It has too many aspects, and it changes, it affects things rapidly. You have a very different image when you use ventilation. So that's, and when you have a train, and you may have on both sides evacuation, so you have to examine exhaust ventilation mainly than longitudinal, because longitudinal may not help you in such case.
Yeah, it helps a little bit in the stratification if it starts working, of course.
Yes, because you may have people in both sides evacuating.
No, but it's very useful, of course, for the tunnel smaller, let's say, than 2 kilometers or 1.5 kilometers, that it's actually no mechanical ventilation in the older tunnels. And again, congratulations.
Yes, thank you. And the other thing you said, what...
7 minutes.
Yes, these 5 minutes, for example, and 7 minutes that I saw you, it's because this is a small tunnel that I examined because of the time of the analysis, because there were many scenarios, but it has effect from the boundary, so if you have a larger tunnel, then the time changes. So this was from this analysis for different geometry for this tunnel length, you can say we have 5 minutes, but you cannot take it very easily to other tunnel lengths. And from the standard, the time is 4 minutes. It's, you know, the NFPA, it's for the station. They say the platform 4 minutes, and the whole station you have to quit in 6 minutes. And I think there are some other standards with 5 and 7 minutes, which they have the available egress, safe egress time. Yeah.
Great. Thank you very much.
Thank you.
Thank you very much. Thank you, Mr. President.
So, we can proceed now with our third speech. The title of this presentation is Seismic Performance of Major Twin Tunnels with Underground Concrete Lining, Expert Witness Study for the Needs of Arbitration. I invite here on the floor Professor Ioannis Anastatopoulos. He is Professor and Chair of Geotechnical Engineering at ETH Zurich. His research focuses on geotechnical earthquake engineering and solid structure interaction. He has been involved as an expert consultant in projects in Europe, USA, and the Middle East. He has served as national delegate for Switzerland for the second Eurocode 7 and member of the SEA 276 Commission. He serves as associate editor for Soil Dynamics and Earthquake Engineering, and also other important journals. So, thanks to be here. The floor is yours.
Thank you very much for the introduction and the organizers for the invitation to present. It's a simple presentation. I mean, you saw the keynote lecture of Professor Pidilakis, so I think this was a good introduction about the problem of seismic loading of tunnels. Usually, tunnels are considered to be less vulnerable than overground structures, but for countries like Greece, of high seismicity, this can be an important problem. So this study was done some years ago as part of an arbitration for a court case. It was a big court case, so this is why I will not reveal which tunnel it was. Okay. The tunnel is situated in Greece. It is a twin tunnel with 2 branches, 6 kilometers length, and a maximum overburden of 300 meters. It is passing through a mountain range we call Ossa, crossing crystalline limestones and phyllites. You see here a cross-section. I will not say a lot about this. It was constructed with a conventional method of excavation, of drill and blast, and the temporary support had a shotcrete combined with some additional support measures, which I will not talk about. The final lining, and this is our problem, this is where the problem came. There were 2 areas of a tunnel. The first area, let's say, where it was crossing good quality rock mass, it was unreinforced concrete. When the quality of the rock mass was worse, it was reinforced. So the tunnel was designed, it was approved, it was constructed, and after it was constructed, the owner of the project disputed, let's say, the seismic safety of a tunnel. There was an expert, a structural engineering expert that was hired by the owner. He did, I shouldn't say he, because this is revealing something, but anyway, the expert conducted a pseudostatic pushover analysis, and assuming elastic response, in this study it was shown that the tensile stresses of a lining for the case of seismic loading exceeded the tensile strength of concrete, and it was concluded that the lining is insufficient. And the question is what you do in such a case. It's already constructed. So you demolish and construct again another lining with reinforcement. So then at this stage we were appointed by the contractor, okay, to conduct a more, let's say, sophisticated study. Of course, this is more than 10 years. It's almost 15 years ago. So perhaps today some of you will say this is not sophisticated anymore. But at this time it was as sophisticated as we could do. So according to the Greek seismic code, the seismicity of the area where the tunnel is, I will not say exactly where it is, it's in what you see yellow. So we're talking about a PGA, peak ground acceleration of 0.16 g. Based on the geology, this is oil category A. And as part of this, let's say, court case, there were also appointed two seismotectonic geology specialists to conduct their studies and tell us what is the PGA that we should take into account. The first one assumed a very large return period of almost 5,000 years, and this resulted to a PGA of 0.35 g. The second one assumed only 975 years return period, and this led to 0.23 g. So which one is correct? The one is more conservative, the other one is less conservative, let's say. So if, in view of international practice, first of all, we did our own, let's say, assessment of this. We thought that these 5,000 years are a bit over-conservative, and there are several examples. I will not mention all of them. For example, the Barty Mertz Tunnel in San Francisco, a very important tunnel, has been designed for 1,000 years of return period. Other examples, like the Acton Preveza Tunnel in Greece, also in a very high seismicity area, more high seismicity area, also 949 years. So based on this, we thought that the return period actually of 975 years, which leads to this 0.23 g, is not a bad assumption. And this is, I mean, our study was based mostly on this. Of course, for important structures like this one, if you assign, based on the Greek seismic code, this 30% increase, then with the 0.16 multiplied by 1.3, you go to 0.21, which is very close to the second seismotectonic study. So enough for PGAs. We need to come up with seismic shaking scenarios, so we have a two-step procedure. First of all, we start with attenuation relations, and I have here some of them, the most well-known, let's say. And with these attenuation relations, you can go from the assumed, let's say, from the second study, magnitude of the earthquake, distance, and you come up with these spectral accelerations with this kind of attenuation relationships. Then the second thing you can do is you take records, real records or artificial records, you do some mathematical modulation, and then with this massage of the records, let's say, in the frequency domain and also in the amplitude domain, then you can come up with records like this that are matching the spectra of this special study. We need a model, of course, a finite element model in this case. The rock mass was modeled with a nonlinear model which obeys the Moore-Coulomb failure criterion. The lining, and here comes the novelty of this study, we use the concrete damage plasticity model, CDP. There are interfaces that allow sliding and separation. And what you see here, these 1D columns, is actually some kind of free field boundaries that allow proper modeling of a dynamic shaking problem. We didn't know exactly how much was the convergence. In the original study, we had to be compliant also with the original study of the tunnel. It was assumed that the tunnel had a pressure of 180 kilopascal, and this is important because we're talking about a nonlinear analysis, and the pressure that comes to the tunnel from the surrounding rock mass will make a difference also to the dynamic response. So for this reason, we consider two different, a lower bound case and an upper bound case you see here. The lower bound assumes 6 millimeters of initial convergence, and this leads to 350 kilopascal here at the crown of pressure. The other one assumes 14 millimeters, so bigger initial convergence, which means less pressure going to the tunnel. The concrete damage plasticity model combines isotropic damage elasticity with tensile and compressive plasticity, so it can model what happens to the concrete. You see here, for example, as an example, the stress-strain curves for the confined, the rent curve, and the unconfined concrete. Here we have mostly, because there is no reinforcement, so we have mostly the unconfined case, and this is why things are worse. How do we know this works? We know this works because we have done some validations, and you see here an example of a validation against the so-called cross-section analysis. So the blue line comes from a cross-section analysis. The red lines is if we calibrate this model and we run the same, let's say, test in Abacus using the CDP model, we get a good comparison. So at this stage, this is what we had. But later, more recently, as part of the PhD of Anastas Zagalianos, we did additional validations And you see two examples here in terms of force displacement response for two different cases. So bending and low shear and bending and moderate shear, and the model looks good. Actually, this is newer, but this is a confirmation of what we did back then was not that bad. Okay, analysis methodology. So what do? We did two different things. First of all, the so-called pseudostatic pushover analysis. And here we apply to our model an angular distortion in a pseudostatic manner. We computed this angular distortion gamma for both cases, 0.24G according to the first study, 0.35 to the more conservative seismotectonic study. So this is one set of analysis, and the second set of analysis, dynamic time history analysis. This is better, it's closer to what happens in the earthquake, but we wanted to do both to also compare our results with what the structural engineering expert did. In both cases, we assumed both elastic lining response, not realistic, but this is consistent with what was done by the other expert, let's say, and nonlinear lining response with a CDP model calibrated as you showed previously. So we start with a pseudostatic analysis. Here we have elastic lining response and the lower bound initial convergence scenario, so higher pressures. And we see here, what you see here is actually the damage of this lining, the permanent lining. We see that there are some locations that we have big tensile stresses. And also what you see here is the various stages of the analysis. So this is the static, the excavation of a tunnel, increasing pseudostatically the acceleration to 0.24 and going to 0.35. And we see that there are some locations where indeed the tensile strength, which is 142 in this case, megapascal, is exceeded. Pseudostatically, what we see here. Okay, so this is with elastic analysis. The second thing that we did, everything you see until here is to be consistent with a structural engineering expert. So here, we did the analysis of a tunnel standing alone, as was done by the other expert, let's say, applying a pushover analysis. Now the lining is non-linear, it is according to the CDP model. And you see here, if this is the force displacement response, you see that about 1.7 millimeters, it fails. This is consistent with what the previous expert showed. There is a crucial thing missing here. The surrounding rock mass. This is the tunnel as if it was an overground structure. There is no surrounding rock mass pushing radially the tunnel. This is a pushover as if the tunnel lining was a building. Okay, so 1.7 millimeters, it fails. So now we go forward. Now we have also the soil surrounding the rock mass surrounding the tunnel. And we see now a totally different response in the presence of a surrounding rock mass. Because exactly this rock mass is applying pressures to the tunnel. You see here for the two scenarios with 0.24G and with 0.35G, you see again let's say, the damage. In the first case, so here wherever you see red is a lot of damage. Okay, red, it's bloody, it's damage. So here you see that with 0.24G we have some damage here and here at the outer periphery. Here it gets more severe. But in both cases, even with the extreme scenario, the second one, there is no collapse mechanism developing because the cracks are at the outside periphery. So they open, but the surrounding rock mass is pressing them together, so there is no collapse mechanism that develops. This is still pseudostatic analysis. We did something very extreme to see what will happen. This angular distortion here, for 0.35G, the most conservative scenario, had one more zero. Okay, so here we took 1 0 out, and we applied a very extreme scenario, 10 times the angular distortion. You see now how this pseudostatic analysis is performed. 10 times the one computed for the more conservative scenario of 0.35G. So again, here, even in this conservative, very conservative, very extreme analysis, we have similar conclusions. We have more damage in more locations, but still there is no collapse mechanism that develops in this case. And the best analysis we could do is the dynamic time history analysis. This is done with the Kalamata record fitted to the attenuation relationships, the spectra we saw previously. And we see now that we have a maximum drift of about 5 millimeters. The permanent drift is negligible, so it comes back, it does recenter, let's say. And the tensile damage in this case reaches, at some locations here, you cannot even see red now, it reaches 0.16. 1 is bad, so 0.16 it is some tensile damage, but not really
Sorry,
bad.
Professor, just 1 minute late.
I know. Thank you. So we have cyclic degradation effects, which are leading to a bit different response, but still it is okay. So the tensile damage does not penetrate deep into the lining, and we don't have any collapse mechanism. So moving to the conclusions, in my last few seconds, we saw that without the beneficial confining pressures of a rock mass, the lining would fail in merely 1.7 millimeters if you treat it like a building. However, if you take account of the beneficial effect of a rock mass, things are much better, no collapse mechanism develops, there is some damage of course, but this is tolerable. And thanks to our study, which does account for the confining pressures and the dynamic nature of the loading, it was possible to settle this technical dispute in a rational manner. And most importantly, it was possible to avoid adding reinforcement to an already constructed tunnel, which would have been extremely challenging, costly, and very resource intensive, let's say, even if it was possible. So with no delay, thank you very much for your attention, and I will be happy to answer questions.
Thanks, Professor Anastasiopoulos. Are there questions from the floor? Okay, over there. You can reach the microphone.
Put me on the stop. Thank you for the presentation. That was very interesting. A simple question. What is the interface between rock mass and structure?
We consider an interface with, let's say, a friction coefficient, no cohesion, so it's like a Coulomb interface. You can do different assumptions then. You can consider it, you know...
That's why I'm asking, yeah.
Sorry?
That's why I'm asking what is the assumptions you...
The assumption was that there is a friction coefficient between, I don't remember the exact number, but there was a friction coefficient between the rock mass and the tunnel. But this was parametrically investigated. We did the same analysis with the interface considered glued, let's say. So we did both.
And there was an interface between the shotcrete and the rock mass, and then for the waterproof membrane, or was attached one to the other?
No, the interface between the temporary support and the permanent lining, we did not model.
Okay, thank you.
Okay. Are there other questions from the room? No more? Okay, thanks. Thanks, Professor.
Thank
So we've got the next one, modeling underground mine ventilation characteristics using artificial neural networks, presented by Mrs. Maria Karayani. Ms. Maria Karayani is a PhD candidate at National Technical University of Athens in the School of Mining and Metallurgical Engineer. She's also holding an MSc in Design and Construction of Underground Works, while her main subject of research is the design, modeling, and optimization of the ventilation system for underground works, and especially for underground mines. Thank you very much. You have 15 minutes for your presentation.
Good evening. Thank you for the introduction. It is an honor to be here and have the opportunity to present our research. The main scope of our work is the modeling of the ventilation characteristics of an underground mine using artificial neural networks in order to attaining the optimal air quality conditions for a selected mine section. It is well known that mine ventilation is a critical module of underground mining and construction projects, being responsible for the well-being and the health of all personnel. Its main goal is to constantly supply fresh air and successfully disperse gaseous pollutants and airborne particulates. The challenges are often significant, and especially in cases where complicating mining or tunneling works are in place, developing a complex ventilation environment. This is often the case in underground mining projects, where mine development is not as straightforward as in construction works, And while the operation of the machine fleet is widespread to almost all areas and not only concentrating in one working phase. So, some of the main goals in mining industry are to ensure better working conditions and to create a safer and controlled underground environment, and in the same time, to increase efficiency and productivity and reduce the ventilation energy consumption and the environmental footprint. And if we take under consideration that about 50% of total cost of electricity is from the ventilation system, it is obvious that the intelligent and rational operation of this system is essential. So, the best way to achieve these goals is by using the ventilation on demand technology, which is the optimization of ventilation system that targets the intelligent and controller supply at the required quantity, at the required quantity, where and when it is needed during mining operation. And machine learning techniques has a great accuracy to do that. Of course, machine learning is nothing else but a brand of artificial intelligence and computer science, which focuses on the use of data and algorithms to imitate the way that humans learn and gradually improve its accuracy. In fact, machine learning as a discipline aims to design, understand, and apply computer programs that learn from experience for the purpose of model, prediction, or control. And there are three main methods: the supervised, unsupervised, and reinforcement learning. In our case, we choose to use the supervised learning because we know exactly what are the target values that the algorithm must predict, and these values are very well and strictly defined by the strictest standard and effect degrees for mine ventilation. And from the machine learning techniques, we choose to use artificial neural networks because of their ability to learn and process large amount of data in a short time frame, the capability of full readjustments the parameters and continuously improving the algorithm, and of course, because of their great performance in dynamic evolving situations, such as underground mines, in which the needs of ventilation change while the exploitation progresses. So, NCPLU ANN consists of the input layer, one or more hidden layers, and the output layer. These layers are interconnected with a specific number of neurons that transfer the signal. The way that all neurons connect to each other, called topology, and it's one of the most important features because the architecture, or topology, determines the capabilities of the ANN. Besides the above, there are also two main characteristics for the composition of an artificial neural network: the training or learning algorithm, which is the method that establishes the values of the weights on the connections, and the type of activation function that defines the output of a neuron for a given input. And last but not least, for the basic theoretical background, the data of every dataset should be split in training, validation, and test set, or in a combination of the training set with one of the rest. So, the ventilation network of the underground bauxite mine neatly identified a map in detail so as to accurately depict in underground workings and recognize the tunnels that are used for the ventilation. In the picture, you can see the layout of the network that was imported into the Vention design software and developed into a 3D working model, including the positioning of all main fans, as well as the exact layering of all auxiliary booster fans and flexible ducts. The blue lines are the main airway tunnels, and the purple lines are the flexible ducts. The model has been validated through its comparison using real data measurements that have been carried out at the mine, both in terms of airflow quality and quantity, and in respect with the permitted limits. A section of the mine was chosen in which there are two productive tunnels, the ventilation of which is provided by the same fan that supplies them with the requirement airflow. In both tunnels, working diesel equipment with a corresponding number of personnel. According to the strict standard in effect in Greece, for diesel equipment is defined at 2.3 cubic meters per second per horsepower, and for personnel at 5.66 cubic meters per second per person. And as you can see in table, the quantity airflow characteristics are in compliance with the permissible limits. In addition to the airflow quantity, the analysis is made also in the air quality characteristics of the selected section. In these diagrams, you can see the results of a 7-hour simulation with respect to the gas pollutants that perform at the working areas. As it's shown, all concentrations are stabilized after the first 3 hours of simulation, while they are within these limits. So, passing now to the development of the ANN model. The aim of the model is to adjust the characteristics of the fan and regulators in order to achieve the optimal air conditions by predicting the nitrogen oxide concentration. The implementation made through the use of a feed-forward artificial neural network and the algorithm written using the Python programming language. As you can see, the input data are the airflow of the fan and the openings of the regulators, and the output data are the gas concentration of the two working areas. The dataset consists of total 229 records for each group data, 80% used for the training and 20% for the test set. Also, the accuracy of the generalization of the model evaluated based on the relative error between the predicted and the actual value of the gas concentration. After many tests in finding the optimum topology, the best model architecture structure with 3 input neurons. Then the first hidden layer consisted of 45 neurons, where a 20% dropout rule was set, following 3 hidden layers with 35, 20, and 10 neurons. And finally, we have 2 output neurons with assessing the gas concentration. As the functions, the ReLU is used as the activation function throughout the model, followed by the linear in output neurons. And also we choose the uptime optimizer, which is a method for stochastic gradient descent in order to adapt the learning rate for each weight of the neural network. And for stopping the training process, we set as requirements either the completion of 2000 epoch or the achievement of the minimum mean squared error in 5 consecutive sensors. At the end of the training, the main task is to check the general behavior of the model. If the ANN responds satisfactory, for example, if it follows the trend of the data and doesn't focus on specific group of values, it means that it's capable for reliable predictions. In diagrams on the right, the orange lines show the actual values and the blue lines show the predicted values. As it's shown, it is clear that in both cases, the model has consistent behavior across almost the entire range of the test set and follows satisfactorily the trend of the true values, which means that it's capable for rational predictions. Also, as you can see in cross-plot on the left, there is a high accuracy degree between the predicted and the actual concentration values. More specifically, the ANN's generalization has an average forecast accuracy of more than 90% for each corresponding location. This is also an evidence that the trained model is successful and the algorithm has the ability to lead to reliable predictions. But the main consideration for the validation of the model accuracy is to check how good is its performance for unknown data. To do this, new data obtained from the ventilation model through Ventism designed, and a total of 5 new random inputs were selected and compared with the obtained results from the ANN model. As it's shown in the table, the check confirms the accuracy of the model as the relative error is under 13%. And more specifically, in case 2, 3, and 4, in 5 values, the relative error is below 2.5%. For the other 2 cases, the model has also a relative error about 10 to 12%. This further indicates the consistent behavior of the model that can now be used for an immediate assessment of the anticipated conditions. So, to conclude, the ventilation of underground exploitations is an indispensable part of the whole mining process. Except of being responsible for health and safety issues, the ventilation system has a major role for the efficiency and the productivity of the project. ANN models has the ability to understand the complex nature of the phenomenon of the gas concentration evolution, along with the ventilation's effect on them. and with their ability to generalize with a forecast accuracy more than 90% regarding the state of the anticipated condition and gas concentration, classified among the best methods for future use. The development of methodology of this research proved that it is possible to utilize a synthetic database derived from a validated digital twin to gather the required data in the absence of real measurements. Such strategies can work well with machine learning techniques to overcome such issues and can assist engineers to adapt operating strategies and come up with a flexible yet resilient and autonomous ventilation system. The formation process can be further developed with the implementation of an autonomous ventilation on demand system that will constantly monitor and control the ventilation system of underground mines. This can lead to a significant improvement of the social license to operate by achieving both a reduction of the environmental footprint of the mines, but also to ensure an upgrade to work safety level. Thank you.
Thank you very much, Ms. Karagianni. Are there any questions from the audience?
No questions, okay, maybe I can ask. I watch results that you research and they are very accurate, but maybe results of zone 2 were more precise, yes, respect to the zone 1. Maybe it was because we had a more complex system in zone 1 as a jumbo plus 2 different persons.
Yes.
It could be.
Can you repeat? I don't hear you.
I will repeat the question. I watched the results that you obtained, and of course they are both zones. You reach a good accuracy of the results. But the results of zone 2 were more precise, maybe because in zone 1 you had a more complex system because a jumbo plus 2 persons respect just the LCD.
The results is about the amount of data, not only if it's complex or if we have more personnel, more equipment.
Okay.
And if I understand, if we have more data, it will be more accurate.
Okay.
That's all.
Thanks.
Thank you.
So we close our 9.3 session. I would like to thank all the speakers, also the audience for the attendance, also my co-chairman for a short and nice collaboration.
Thanks.
Thank you.
Thanks, Nico. Thanks to all.